Hi all, welcome back to our discussion on quasi-geostrophic theory. Today we'll be looking at Part 4, the geopotential tendency equation. So we'll be looking at an extension of our analysis of synoptic scale waves from the first three parts in order to examine how exactly geopotential will be evolving in those waves. So recall vorticity and geopotential. In particular, we have so far derived a quasi-geostrophic vorticity equation, which consists of three terms: one a stretching term, and two advection terms. One representing advection of relative vorticity and one representing advection of planetary vorticity. We showed that depending on the wavelength associated with these waves, that whether relative vorticity advection dominates or planetary vorticity advection dominates, you'll get either eastward or westward propagating waves. Now, we're going to use the geostrophic wind relationship and the geostrophic vorticity in the form of a geopotential. In particular, recall that the geostrophic vorticity can be related to the geopotential via 1 over F naught times the Laplacian of the geopotential. So we're going to start from this form of the quasi-geostrophic vorticity equation where advection of relative vorticity has been absorbed into a material derivative of relative vorticity. Then using the fact that relative vorticity can be written in terms of the geopotential, as shown on line 2, we have then obtain a form of the vorticity equation shown on line 3. Then expanding out the material derivative, we see that it takes the form on line 4 here. Now we're going to define a term, the geopotential tendency, via this Greek character chi, and it is simply going to be the Eulerian rate of change of the geopotential. That is, the rate of change of the geopotential at a specific point. Then using the previous form of the quasi-geostrophic vorticity equation, we then obtain a expression for geopotential tendency shown here. So this combines both geostrophic terms, which includes the left-hand side and the first term on the right-hand side, plus an ageostrophic term, which is associated with stretching. Recall that divergence of the horizontal velocity field is due to ageostrophic motion, and that is what is going to be responsible for driving vertical velocity and stretching. So taking this expression then, using the geostrophic wind relationship to write the geostrophic wind then in terms of geopotential, we then obtain this form below for a quasi-geostrophic geopotential tendency equation. Note that the only unknowns in this equation then are the geopotential phi and omega, which appears in the stretching term on the right-hand side. So this expression, in the absence of vertical motion, can then be used in order to actually evolve the geopotential field directly. So for the previous derivation of the geopotential tendency, we use the first three equations from quasi-geostrophic theory. Recall, however, that there are four equations, the fourth equation being the thermodynamic closure, which is obtained from advection of temperature. This fourth equation will then be used in order to eliminate omega from the quasi-geostrophic geopotential tendency equation. So for baroclinic systems in particular, all four equations must be used in order to derive a closed form system. The first three equations are again sufficient for barotropic systems where we have no stretching associated with the motion. So our goal then is to replace this last term in the geopotential tendency, and we're going to do that by using the omega that appears in the quasi-geostrophic thermodynamic equation. So first of all, we're going to start with the thermodynamic equation as shown here on line number 2. We're going to flip the derivatives and use the fact that we have defined this geopotential tendency, chi, in order to write this first term then as just the pressure derivative of the geopotential tendency. So then taking this equation and taking F naught over sigma times the pressure derivative, applying that composite operator to the whole equation, then leads to a form of the thermodynamic equation that looks like the bottom line. Note here that we have now obtained a term that looks like F naught di omega di p, and that will be used then to cancel out the term in the geopotential tendency equation. So geopotential tendency equation from before appears like this first line. From the thermodynamic equation, we have this second line. In particular, observe that these two terms have opposite sign, but similar character associated with them. And in particular, note that the only independent variable that appears in the thermodynamic equation is the geopotential, assuming that J is prescribed. So if we take these two equations and add them together, that will then eliminate the omega term from this equation. This then leads to what is known as the adiabatic quasi-geostrophic geopotential tendency equation. Here we have assumed that J is equal to 0. However, this is not a necessary assumption within quasi-geostrophic theory. So this leads to three terms, all of which look fairly complicated in mathematically. However, we'll see that they actually decompose fairly readily into very simple qualitative concepts. So this left-hand term here is a complicated composition of second derivative operators, but this basically just represents the local geopotential tendency. This operator is one that we'll need to invert then in order to solve for the local geopotential tendency. The first term on the right-hand side is basically proportional to absolute vorticity advection, the only difference here being that it is multiplied by an F0 term, which is simply associated with the sign of the hemisphere. The term on the far right-hand side is a new term, which is not unlike anything we've seen before, and this is actually proportional to basically differential thickness or temperature advection. Recall that thickness and temperature are inherently related to one another, so whenever you see this partial derivative of geopotential with respect to pressure, you can imagine that is basically corresponding to a layer thickness or a temperature of that given layer. So when you see minus UG dot that is associated with advection of layer thickness. And in particular, we're looking at vertical shear of that particular quantity, hence the addition of the additional pressure derivative here immediately before that expression. So one thing that's very exciting about this is that only the initial distribution of the geopotential needs to be known in order to perform a forecast using this equation. That is, the only independent variable that shows up in this equation is the geopotential phi. Now we're going to look closer at these second derivative terms. In particular, for large wave-like flows, such as those described by trigonometric functions, sines and cosines, you'll observe that simply taking the second derivative of these expressions is effectively equivalent to multiplying the expressions by -1. Hence, when we see this expression for the geopotential tendency on the left-hand side of the QG geopotential tendency equation, we can simply say that that's a fancy way of writing a minus sign, and then in addition to an additional proportionality constant. So let's look back for a moment and say, okay, what's the point of our looking at the quasi-geostrophic geopotential tendency equation? Recall that we want to perform forecasting, that is, given an initial geopotential field, we want to be able to determine how the geopotential will evolve into the future, and in particular, we're interested in forecasting as applied to two major weather phenomena in the mid-latitudes, large-scale waves and mid-latitudinal cyclones. So let's look at large-scale waves at first. So we have absolute vorticity advection as the dominant term in the quasi-geostrophic geopotential tendency equation, because for barotropic flows we anticipate there to be no differential temperature advection. So this equation then looks like a simplified form of the quasi-geostrophic geopotential tendency equation from earlier, and simply looks like geopotential tendency is evolved in accordance with advection of absolute vorticity times F0. So looking at this in the context of an upper tropospheric wave, recall from earlier that in the red region we had that advection of relative vorticity is positive and advection of planetary vorticity is negative. Hence this corresponds to short waves, hence for short waves this corresponds to relative vorticity advection being dominant, and hence advection of absolute vorticity being generally positive. For short waves, recall that we're going to observe a eastward tendency associated with this wave. This is mirrored similarly in the blue region, where we have negative advection of relative vorticity and positive advection of planetary vorticity. So for short waves, we then have that advection of relative vorticity is dominant, and so advection of absolute vorticity is negative. So this corresponds then to eastward propagating waves. If you look back at the quasi-geostrophic geopotential tendency equation, you will then see that advection of absolute vorticity being positive corresponds to a negative tendency of the geopotential in the red region and a positive tendency of the geopotential in the blue region. So this actually corresponds to rightward propagation of the wave, analogous to how we saw advection of relative vorticity previously. That is, we're going to see in the red region that there is a decreasing geopotential, and hence the location of that low will tend to shift eastwards following the wave. Analogously, in the blue region, you're going to see a positive tendency of the geopotential. Geopotential is then increasing in the blue region, and so the local high will then tend to propagate eastwards as well. For long waves, we have the opposite, namely there's negative advection of absolute vorticity in the red region and positive advection of absolute vorticity in the blue region. From the standpoint of the geopotential tendency equation, this then indicates that in the red region, you're going to have increasing geopotential, and in the blue region, you're going to have decreasing geopotential. Consequently, you're going to see a westward propagation of the wave. So for short waves, when we have advection of relative vorticity, being larger, then you're going to see eastward propagation of the wave, and for long waves, when you have planetary vorticity being larger, you're going to see westward propagation of the wave. So let's now look at mid-latitude cyclones. So we're going to extend now and start to look at the development of an extratropical cyclone from a large-scale mid-latitudinal wave. So the evolution of extratropical cyclones then requires looking at the differential temperature advection term. So this is the new term that we've now observed in deriving the QG geopotential tendency equation. And it basically looks like a shear of thickness advection. So the question then is, why is thickness advection proportional to temperature advection? And the answer being simply that thickness and temperature are inherently related to one another. So for differential temperature advection then, our geopotential tendency equation then looks like this, namely simply the shear of the advection of temperature. And so when we have differential temperature advection below 500 hectopascal, that is near the surface, this has a tendency to when we have positive differential temperature advection in this region, we then have a tendency to build a ridge, increasing geopotential, which is associated with decreasing warm air advection with height. Or if this term is negative, then this has a tendency to deepen the trough, decreasing local geopotential, and this is associated with decreasing cold air advection with height. So thinking about this in terms of warm fronts and cold fronts then, for warm fronts, we have that there is a increase in warm air advection with height, whereas for cold fronts, underneath the cold front itself, we observe that there is a decrease in cold air advection with height. So for extratropical cyclones, which are important for driving weather in the mid-latitudes, these are closely associated with weather fronts, and so we'll observe that this differential temperature advection is relevant when it comes to analyzing these weather fronts. So looking at this on a map from above, you'll notice that the trough region associated with the geopotential wave is typically associated with cold air advection, whereas the ridge associated with the geopotential wave is associated with warm air advection, where the kinked low is then located roughly halfway along the wave. So cold air advection then to the west of the surface low will have a tendency to enhance the trough, whereas warm air advection east of the surface low has a tendency to enhance the ridge. Viewing this in the context of the Norwegian cyclone model, as the wave becomes a mature low pressure system, while the cold front is moving faster than the warm front, it then catches up to the warm front. So this is the case where we leave the linear regime then and enter into the nonlinear regime. So if thickness advection then is proportional to the negative of the height derivative of temperature advection, and vorticity advection is proportional to the advection of absolute vorticity, we then can see that geostrophic advection of geostrophic vorticity will cause the wave to propagate. That is, it has a tendency to not increase the overall magnitude of the wave itself, whereas the presence of temperature or thickness advection causes the wave to amplify. All right, so now we're going to look at a complete model of a baroclinic instability combining both the surface view and the upper level view. So in the upper level view, we have a typical wave-like pattern, an upper level tropospheric wave analogous to the upper level tropospheric waves that we've looked at previously. Here on the lower level, however, we have a developing baroclinic instability with the characteristic kink being observed in the frontal systems. So you have the existence of the warm front extending eastward from the surface low and the cold front extending to the southwest away from the surface low. As you can see, this system has the characteristic westward tilt associated with the baroclinic instability. That is, the upper level low is located to the west of the surface low, and analogously with the upper level high and surface high. The presence of ageostrophic motion near the surface is responsible for driving convergence at the surface and upper level divergence as that air is being transported upwards. So this leads to vertical velocity at the center of the low, hence leads to intensification of the extratropical storm as the column is stretched and vorticity is generated at the location of the low. We have characteristic precipitation also appearing at the surface near the fronts. We have this elongated precipitation system associated with the warm front and a more extreme localized precipitation associated with the cold front. So the vertical stretching leads to basically increases in the vorticity field, but the vertical stretching is also responsible for enhancing the geopotential field. That is, by increasing the layer thickness in these regions, we're also increasing the differential of the geopotential with respect to horizontal distance, and consequently leading to intensification of the underlying geostrophic winds, and hence connected with this intensification of the vorticity. So at the upper level, we have vorticity advection in both the convergent and divergent regimes, and we'll delve into this in more detail later as we explore the omega equation, which governs vertical velocity of the flow. We also have thickness advection, which is going to be located to the east of the surface low, and that is going to be responsible for intensification of the ridge, whereas thickness advection to the west of the low, that is cold air advection, will be associated with deepening of the trough to the west of the system. Hence, we get that the baroclinic instability, which has this characteristic wave-like pattern to it, will tend to intensify and the magnitude of the wave will increase. So the westward tilt associated with this system is basically acting on conservation of energy. That is, the westward tilt allows for energy to be transported northwards to the east of the system and southwards to the west of the system, but further it is also connected with the production of entropy. That is, an eastward tilt associated with the system will actually lead to a weakening system overall, and hence greater organization of the overall system. Hence, entropy will be decreasing if an eastward tilt is present in the system. The westward tilt, however, is associated with entropy generation, that is, mixing of the fluid. And so the westward tilt is effectively necessary from a thermodynamic point of view, although we will not delve into this in further detail here, but that will be covered in a later dynamics class.